Hi guys, so today we are looking at lesson 2-3 and we are going to be looking at graphing a quadratic function with an a value, and when I say that I mean an a value other than 1. So the graphs that we've looked at in both 2-1 and 2-2 both had a values of 1. Whether they be positive or negative is another story, but the a value was 1. So for our essential question, you need to describe how an a value other than 1 affects the graph of a quadratic function. So before we get to our vocabulary, I want to go through some exploring problems again. So the first equation we have here is y equals x squared, and I hope you can all tell me what the name of this equation is called. This is our parent function. And remember, the parent function is the simplest graph of any type of function. So y equals x squared is the simplest quadratic function. So with the parent function, we found that when we plug our numbers into the equation, our x values that is, when we plug these x values into our equation, these are our output values or our y values. So if we plug in -3 to the second power gives us a +9, -2 to the second power gives us a +4, etc., etc. So we've already found these values on a couple of different occasions, mathematically minded. So over here, what we want to do is take a look to see how this a value of 2 is going to affect our numbers. So what we're going to do here together is we're going to take these x values and, just like we did over here, plug them in to the equation to see what our output values look like. Before we do that, though, I want you to take a few seconds and say to yourself how you think this is going to affect our y values. All right, so what do you think is going to happen? Let's see what actually happens. So if I take this x value and I substitute it into my function, I have y equals -3, excuse me, erase, y equals 2 times -3 to the second power. Now, don't forget, you have to follow your order of operations. You cannot multiply until you have used your exponent. So we have our order of operations, PEMDAS. Okay, we have to do parentheses. Well, there's no operations happening inside the parentheses. Then we have to do exponents, and we do have an exponent here. So we have to use the exponent on the -3. So this is -3 times -3, which is a +9. And then 2 times 9 gives us 18. Same thing with -2. Y equals 2 times -2 squared. -2 squared is -2 times -2, which is a +4. And 2 times 4 gives us 8. Same thing with -1. -1 squared is -1 times -1, which is a +1, and 2 times 1 gives us 2. Then if we plug in 0, see if I can fit this in here. 0 squared is 0, and 0 times anything is simply 0. So those are our negative values and our 0. Let me make some room and we can plug in the rest of our values. Sorry, that takes forever. I don't want to clear my whole screen and then lose my table of values. Okay, so if we plug in +1, we have y equals 2 times 1 squared. 1 squared is 1 times 2 gives us 2. And notice we can see where our vertex is because our y values are now repeating. We have 2 times 2 squared. 2 squared is 4, And 4 times 2 gives us 8. And our last one is 2 times 3 squared. 3 squared is 9, and 2 times 9 is 18. So you can see where our graph turns around, indicating that this is, again, our vertex. So how do these values differ from what we had for the parent function? So in our parent function, when we plugged in -3, we got a +9 as our y value. So if you take a look at what we have when we had an a value of 2, well, how did that affect our y values? Well, 2 times 9 gives us 18. 2 times 4 gives us 8. 2 times 1 gives us 2. 2 times 0 gives us 0. And again, it repeats. 2, 8, 18. So when we have that a value out in front of our graph, how does that change our graphing pattern? Because remember, our graphing pattern are those 1, 4, 9 numbers. Those are our perfect square numbers. So how do you think a value of 1/2 is going to change our numbers? Well, if you said it's going to give us half of the y values, then you're absolutely correct. But let's check that out and see how that works. So if I plug in -3 to this equation here, we're going to have y equals 1/2 times -3 squared. -3 squared is a +9, and 1/2 times 9 is 9/2, or 4.5, 4.5. Well, 4.5, or 9/2, is half of 9. Now, just really quick, I just want to talk really quick about multiplying 1/2 times your whole numbers. So if we have 1/2 times 9, remember this 9 is a whole number, so this is over an invisible 1. So if I multiply this out, when we multiply fractions, we multiply top to top and bottom to bottom. And so that gives us 1 times 9, which is 9, over 2 times 1, which is 2. Now you can leave this as 9/2. You can leave it as 4.5, whatever you want to do. We just need to make sure we understand that that is half of 9. So for the -2, we have y equals 1/2 times -2 squared. -2 squared is a +4, and 1/2 times 4 is a +2. Y equals 1/2 times -1 squared. -1 squared, -1 times -1 is a +1, times 1/2 is 1/2, or 0.5. Y equals 1/2 times 0 squared. Half of 0 was still just 0. So there's our vertex again. And our values will be repeated. I'll spare you the work through those. So what I want you guys to see here is that when you have that a value out in front of your equation, that's going to change our graphing pattern by taking our graphing pattern and multiplying it times the a value. So again, we don't have to go through the process of plugging in all of these values every time. If we're able to understand that it just affects our graphing pattern by multiplying the graphing pattern by the a value, then that saves us a lot of work. So what we have to remember first is that our graphing pattern is 1, 4, 9. 16, 25, etc. We have to remember that. If we don't know that, then we will have to go through the process of plugging in our numbers into the table of values. But the second thing to remember with that is when we use the graphing pattern, say for the 9, that is, well, let's start with 1. So we have our vertex here at 0, 0. So our next point from there is up 1 and over 1. Our next point from there is up 4 and over 2. And our next point from there is up 9 and over 3. Now this always goes back to the vertex. So when I say you're going up 1, you're going up 1 from the vertex. When I say you're going up 4, you're going up 4 from the vertex. And then the over numbers, you're going to go over 1 from the axis of symmetry, over 2 from the axis of symmetry, over 3 from the axis of symmetry. So over here, for the graph where the a value is 2, from the vertex, we're going to now go up 2 and over 1, up 8 and over 2, up 18 and over 3. For the graph where the a value is 1/2, we will go up 1/2 and over 1, up 2 and over 2, up 4 1/2 and over 3. And again, those always go back to the vertex to go up, and from the axis of symmetry, you go over. Well, let's take a look at how this will look graphically. Technical difficulties, excuse me. Okay, so we have y equals x squared, which we know is our parent function. We know the vertex of the parent function is at 0, 0. And again, that graphing pattern is 1, 4, 9. Now I just wanted to look at this again and refresh the graphing pattern. How to use that from the vertex? Well, the 1 is our first one. So we go up 1 and over 1 from the vertex. So up 1 and over 1. Then going back to the vertex, we're going to go up 4 and over 2. 1, 2, 3, 4, and over 2. And then for the third one, up 9 and over 3. So up 9 and over 3 for that third point. Make sure we draw our axis of symmetry. Typically speaking, it's a better idea for us to draw that before so that we have the axis of symmetry as a reference. But in this case, it was my y-axis, so that made it a little bit easier. So there is our graph of the parent function. Again, our graphing pattern, 1, 4, 9. That's 1 over 1, 4 over 2, and 9 over 3. If we had room, our next one would be 16 over 4. So just real quick, a few vocabulary terms. Just refresh. Vertex form is the equation y equals a times x minus h squared plus k. Now remember, the h and the k are our vertex. And we saw how the h and the k values shift or translate our graph, h horizontally and k vertically from the origin, from 0, 0, which is where the vertex of the parent function is. Now, what we haven't talked about yet, which we just saw, is that a value. And that a value affects our graphing pattern. And that's going to cause us to increase the distance from our vertex for each point or decrease the distance from our vertex to each point. So if we have y equals x squared, our parent function, notice that there's no h value and there's no k value here. So when there's nothing being added or subtracted to the x, and there's nothing being added or subtracted at the n, that indicates that our vertex is at 0, 0. Now in this case, our a value is that invisible 1 there. So we're going to see some equations today where we'll still see that vertex at 0, 0, but we're now going to see a different a value. That a value is going to cause our graph to either shrink or stretch. And we're going to talk about that more within our guided practice problems today. But these are the two words that we need to refer back to when we're describing the transformation of our graphs: shrink or stretch. And then lastly, just make sure we understand and we note that our graphing pattern is 1 over 1, 4 over 2, 9 over 3, 16 over 4. And this is the graphing pattern of our parent function, as we just saw in the explore problems. That's going to change based on the a value. But I'm going to refer back to this graphing pattern, and this is something that we definitely need to be familiar with. I want you guys putting this in the margin nice and big, highlight it, whatever you need to do so that you see it and you remember it.